Welcome back to the next subtopic, 10.3, sound intensity. So for the sound wave introduction, sound waves are produced by vibrating source such as a guitar string, human vocal cords, prongs of a tuning fork, or a diaphragm of a loudspeaker. So for example, when we hit the drum, the membrane of the drum vibrates will produce sounds. Or when we play the guitar, the string on it makes to and fro motion and produce the sound. Or even we can have the sound produced by the vibrating prongs of a tuning fork. So the sound waves are mechanical and longitudinal wave which needs a medium for its propagation. The sound wave propagates in any kind of medium through a series of periodic compressions and rarefactions of pressure which is produced by the vibrating source. So the distance between the two centers of the compressions and rarefactions represent the value of the wavelength lambda. So from diagram here, it shows that the compression part is the high pressure part and the rarefaction part is the low pressure part. And here is the direction of the wave propagation. And this is the wavelength. The sound propagates in 3 dimensions. Crest of the wave form a series of concentric spherical shells indicated by the blue circles separated by wavelength. The rays indicated by the red arrowhead indicates the direction of the propagation. Next, for the sound intensity, with the symbol capital I, is actually perceived by the ears as the loudness. So the definition of the sound intensity is energy transported per unit time across a unit area which is perpendicular to the direction of wave propagation. So we have 3 equations here. Basically, we have intensity equal to the power over area, and for the power is defined as the energy per time, and also we can have area equal to 4 pi r squared. So basically the intensity is a scalar quantity. Its SI unit is a watt per meter square. So the intensity of a sound wave is uniformly distributed at the same distance. For 3T wave, the area a sound wave travels through is a sphere. Here we have the dependence of the sound intensity on the first one, amplitude. So the intensity is directly proportional to the square of the wave amplitude. So small amplitude corresponds to low energy wave, which means low intensity. And large amplitude corresponds to the high energy wave, means high intensity. So the graph here shows that if we have lower amplitude, there is a quieter, and we have a louder, means we have the higher amplitude. Here is a graph of intensity against amplitude. We have a curve. So if we want to have a straight line graph, we can have I versus A square with the relation I1 over I2 equal to A1 square over A2 square. The second one is a distance from the point source. So the intensity of a sound decreases as you get farther from the source of the sound. Intensity is inversely proportional to the square of the distance from the point source. So we have I is inversely proportional to R square. So meaning the relationship can be illustrated by the figure above. The energy twice as far from the source is spread over 4 times the area. Hence 1/4 the intensity. So here is a graph of intensity against R distance. We have a curve here, meaning as the distance R increases, the intensity will decrease. And for the graph of I against 1 over R square, we will get a straight line graph with the relation I1 over I2 equal to R2 square over R1 square. Now let's try example 3. A small source emits sound wave with power output 80 watt. Find the intensity 3 meters from the source. To get the value of intensity, we can simply apply the formula power over 4 pi r squared and substitute the value of R equal to 3 meters to get 0.7074 watt per meter square. Second one, find the distance at which the intensity of the sound is 1 to the power negative 4 watt per meter square. To get the value of the distance, we can still using the same formula, whereby we substitute the value of intensity given, the value of power given, and to get the value of R equal to 252.3 meters. And for question C, at what distance would the intensity be 1/4 as much as it is at R equal to 3 meters? So we know that the relation between the intensity and the distance is I inversely proportional to R squared. So we can have the ratio I1 over I2 equal to R2 squared over R1 squared. So substitute the value of I2 equal to 1 over 4 I1, and we can cancel out the I1 later on. And we can have the value of R1 is 3 meters to get the value of R2 equal to 6 meters. So here's the end of the video. We will proceed with the next subtopic in the next video. Thank you for your watching.